After looking at exponential patterns in the last couple of weeks, you might have noticed that one thing about exponential patterns is they tend to produce really big or really small numbers. Things grow really, really fast, or they are getting smaller at an exponential rate. You tend to deal with often larger or smaller numbers than you usually would with linear patterns in some cases. And again, we're in a great situation right now with a pandemic. Not great in the sense of what's going on Earth right now, but it's just good timing with what we're studying because one of the best examples of exponential patterns and dealing with things that involve exponential, these really large or really small numbers, those things tend to arise naturally when we're looking at a situation like we have right now. So this cell division video shows you that at first it's not going that fast, but at some point it just sort of blows up. And that's that characteristic of exponential patterns, is that sort of explosive growth that we often see. And then you get really, really large numbers really, really fast. Things kind of blow up on you. And so with this one, we're looking at E. coli cells because the way cells reproduce is often through just splitting. Single-celled organisms, they're in good conditions. They just, one cell splits into two cells. Each of those two cells splits into two cells, and so on. And so a little bit of E. coli ingested can turn into a huge E. coli population in your stomach that can be toxic and even deadly. And so the first one is just tinkering with some of those numbers to see just how quickly those numbers get larger. So this is really just a substitution problem. So each time on this one, you're solving the equation 1,000 times 2 to the power of x to get the number at each time. And just be careful, this is doubling every 12 hours, which means it's twice a day. So that means in 1 week, we're going to have 14 doublings. So 1 week goes with this calculation down here where it's 14 doublings. So 1,000 times 2 to the power of 14. 2 weeks, that's 14 days. That would be 28 times that the cells would split and double. So that's that calculation there, 1,000 times 2 to the 28th power. And the final one, the really big one, in 1 month, if a month was 30 days, that would be 60 times that it would double. So you've got that, 1,000 times 2 to the power of 60. And you get some really massive numbers. And depending on the calculator that you're using and the settings on that calculator, you may have gotten numbers like these, or you may have gotten your numbers in scientific notation. So you might, and it's okay to round these off when you're writing them. You don't have to write down every single digit. It's okay just to write the first handful of digits and fill the rest in with zeros. So you may have gotten 1.68. And a lot of calculators will use an E for scientific notation. So they'll do like E7. And remember what that means is this is 1.68. And the E infers times 10 to the power of 7. So it's 1.68 times 10 times 10 times 10 times 10 times 10, and so on, 7 times. So this second one would be like 2.68. And then you may have had E11. And so remember that's times 10 to the 11th power. And then this one would be 1.15 times 10 to the 21. Again, that your calculator may not have done that, but if you had one that had that E or something like that, some weird notation, what it's trying to show you is that this is a really large number and your calculator can better fit that number into the screen that it has if you use a scientific notation to condense it. And that's what scientific notation is for. It takes these huge numbers, like that top one with all those place values, takes huge numbers or very small numbers and writes them in, first of all, a smaller way. So it doesn't include as many digits and as many place values, doesn't take up as much room. But we're also going to find this week, as you go through investigations 4, 5, and 6, that if you leave your numbers in these scientific notation forms, scientific notation has an exponential piece to the number, a 10 to a power, which is an exponential term, you can actually use some shortcuts in that exponential notation to do math with these really big or really small numbers without having to punch a whole bunch of zeros or place values or whatever into a calculator to do so. There's some shortcuts that really save you a lot of time and simplify those problems. So you may have learned about scientific notation before, but I wanted to do a review of what scientific notation is and why it's written the way it is. So I'm going to use that example of the one that we got for the 1000 times 2 to the power of 14, the number of cells after 1 week of doubling every 12 hours. And use that number as our example. So the original number that we got, I'm going to round it off a little bit, was 16,384. Sorry, 16,384,000. And they call this standard form. All the decimal or all the place values are included. This is just standard form. In this number, that number, sorry, with this number, that form isn't too difficult to work with. You've only got 8 place values to deal with. But notice, as those numbers get bigger and bigger, it really becomes impractical to deal with a number in its standard form at some point. And so what we can do is we can write that in scientific notation. So 1.68, like I said, I'm going to round off a little bit, times 10 to the 7th power. So they call this scientific notation. And scientific notation has 2 parts. So the first part is what I just call sort of the value, the digits. It's telling you how many of a certain sized unit you have. And the size or the scale of that number is written separately. So the 10 to the power of 7, this is the scale of that value. So scientific notation separates the value itself from how big it is. And so you can think of this 10 to a power as kind of being like a unit. Like it's easier to think of this when you use the metric system. So like you can have millimeters, centimeters, meters, decameters, kilometers. Those prefixes are basically telling you what power of 10 the unit is for that value. So if you have a distance that was, well, for example, 2 kilometers, the kilometers tells you that you don't have 2 millimeters or centimeters or something. You have 2 kilometers, which would be 2 groups of 1,000 meters. And the value itself, in order to keep it easy to work with, the value itself is always, and this is just sort of a mathematical convention that was adopted to make scientific notation sort of have clear rules to go with it. It is always a number between 1 and 10. So the decimal is always going to be placed in the spot that makes that value between 1 and 10. So it's 1 or greater and always less than 10. So you wouldn't write this 1.68 as 0.168. You wouldn't stop between the 6 and the 8 and write this as 16.8. We make it a number between 1 and 10 because numbers between 1 and 10 you can kind of do mental math with. They're just a lot easier to deal with. And so that's one of the conventions. Now the reason they use a power of 10 to describe the scale of the value is because we have a base 10 number system, which just means that our number system is based on groups of 10. Our place values when we write numbers. So it takes 10 ones to make a 10, it makes 10 tens to make a 100, it takes 10 100s to make 1,000, and so on. It always takes 10 of one thing to make one of the next unit up, or the next place value up. And so we always use powers of 10 to describe that. So if I took an example, and I'm actually going to start it down here. So let's say we had a number like 25. And we multiplied it by 10 once, we would have 250. So when you take a number and you multiply it by 10 or any multiple of 10, so 10, or sorry, not multiple of 10, but power of 10. So if you multiply anything by 10 or 1 or 100 or 1000 or 1000th, it doesn't change the actual digits. So our 25 is now 250. We still have the 2 and the 5 next to each other. It's just that we've moved the decimal place over once when we multiplied it by 10. So we use these powers of 10 to describe the scale of a number because every time you multiply or divide something by a power of 10, the digits don't change, their place values just change. So continuing this, if I was to, let's say, take my 25 and multiply it by 100, which is 10 times 10 or 10 squared, I'm going to have 2500. So this time my decimal moved over to there. Do this one more time just to make sure you see the pattern. 25 times 10 to the power of 3. So 10 times 10 times 10, that's 25 times 1000. Our decimal is now moved 3 places over. Now I left a gap up there above these because we're also going to talk about what happens when our exponent on the 10 is less than 1, so when we go into negatives. But first, see if you can practice this a little bit and turn each of these numbers either from standard form to scientific notation or from scientific notation to standard form. And then the next video will have a little bit of guidance on checking your work and some of the things to look out for when you are doing those.